This is not a pretty picture, but it is reality. Across the globe, over 3 billion waste tires currently litter our environment. These tires present an environmental hazard. They are readily combustible, and when they burn, it's almost impossible to quench the fire. Tire fires cause serious damage to the air, ground, and any nearby structures. A recent tire fire shut down a major highway in Philadelphia for several months and cost taxpayers millions of dollars. The problem continues to grow. Over 250 million tires are discarded in the United States alone every year. Similar tire problems exist around the world. But now, there is an environmentally sound solution which virtually eliminates the problem of waste tires. Let's take a closer look at how the pyrolysis process transforms waste tires into marketable products. The process begins here. Tires are brought to the plant and rolled down a chute to an automated shredding system. The tires pass through the shredder and are reduced to a 2-inch particle size. Oversized particles are extracted and returned to the shredder for additional shredding. Here we see a simple diagram of the first stage of the process. The tire chips are now delivered in large quantities to a vibratory feeder. The feeder meters the chips onto a conveyor belt at a carefully controlled rate. And the conveyor transports the shredded tires to the reactor. The pyrolysis process delivers the chips to the reactor through a set of airlocks, which prevent oxygen from entering the reactor. When the tire chips are heated in the reactor, the material breaks down to produce a stream of hot hydrocarbon vapors and a stream of solid materials, primarily carbon black and steel. Each of these two streams is extracted from the reactor and processed separately. The hot hydrocarbon stream consists of vaporized oil and combustible gas. As a first step, solid impurities are removed by passing the stream through a spray cleaning system. The stream is then drawn through a large condenser, which lowers its temperature, causing most of the oil to condense. The oil is then drawn from the bottom of the condenser and stored. Here we see a sample of the oil being taken from a storage drum for analysis. The remaining gas is extracted from the condenser and pressurized. Some of the gas is fed to the burners in the pyrolysis reactor. Once the pyrolysis process begins, no outside source of fuel is required to operate the plant. The remainder of the gas can be used as a fuel to make steam or to generate electricity. To illustrate how cleanly the fuel burns, observe these 3 stacks on the roof of the plant while the reactor is operating. One of these stacks is disconnected. The pyrolysis process is so clean that the operating stacks cannot be distinguished from the dormant stack. The excess gas is capable of producing enough energy to generate 5 million kilowatt hours of electricity per year. Because the entire process is controlled by a state-of-the-art microprocessor control system, the reactor requires only 2 operators on an 8-hour shift. This diagram represents the processing of the hot solid stream. The solid stream is discharged through airlocks into a water-cooled auger, which cools the material and transports it to a magnetic separator. Here, the steel is extracted from the carbon black by an electromagnet and discharged to a collection box. The carbon black is then conveyed to a bagging station where it is collected in 1,000-pound sacks, removed, weighed, and stored for future shipping. The carbon black is tested in the laboratory to assure quality control. A single pyrolysis unit can recycle more than 650,000 tires per year, and a large plant with multiple units is often used for greater productivity. The sale of byproducts, plus front-end fees for accepting tires, known as tipping fees, generate enough income to operate the plant, repay debt service, and achieve rates of return on equity